Let's understand injections and surjections in the context of vector spaces, right? Once again, there's a very common trend that's going on here is we took all of these concepts and we studied them for Euclidean space, right? Or maps from Rn to Rm or vice versa, whatever, right? And we had these notions of what's a transformation, what's a linear transformation, what does it mean if it's injective or one-to-one? What's it mean if it's surjective or onto? What's an isomorphism? All this stuff, right? We're doing this, but on a stage that's more abstract, right? So that it could appeal to a larger audience. Let's start with injective, right? So let's just recall our definition here. So we have two vector spaces, V and W. And let's define a couple elements of the domain. So we'll have V1 and V2 are in the domain V. T from V to W, this linear transformation is injective or one-to-one, right? We say one-to-one if V1 not equal to V2 implies that T of V1 is not equal to T of V2. We're used to the contrapositive of this last implication, so equivalently, right? This were to say if T of V1 is equal to T of V2, that implies that V1 equals V2. This is the criteria we're much more used to working with to prove injectivity, right? Well, if you have 2 points in the domain, if you have 2 points in the image that are equal, well, then the points or the point that those 2 points were mapped to must be the same point, right? And so remember for injective maps, here's V, here's W. For injective maps, you do not get something like V1, V2, and then, under T, maybe here we have like T of V1 equals T of V2. This cannot happen if T is injective. It's 1-to-1, right? This picture I've drawn here is 2-to-1. It took two elements and it mapped it to the same spot. That is not an injection. That can happen if the map is a surjection, but it cannot happen if the map is an injection. So, right, this is something that never happens for an injective map. It's not that it can't happen for any linear transformation. It's just not one that happens for injections. And that's exactly this criteria here. It's saying the only way that this picture could be valid is if T2 was equal to T1, right? Or excuse me, V1 is equal to V2. This can happen and should happen for an injective map, right? So I just wanted to clarify that there. So let's clear all this. Okay, we learned a lemma, and we've proven this lemma in the context of Euclidean space, where the domain and the codomain were Rn and Rm. So I won't prove this in general. It's not a bad exercise to try and reprove this. We have the lemma that T from V to W is injective or 1-to-1 if and only if T of V equals 0 implies that V equals 0. Remember? So injective functions are those which send 0 to 0, and that is it, right? You don't have some non-zero vector being mapped to the 0 vector. You cannot have that for an injection. Reworded in the context of the kernel, this is if and only if, right? The kernel of T is trivial, meaning the kernel is one element, and that is the additive identity, right? This would be the additive identity here of V. This would be the additive identity of W, right? Because again, a priori, they could be different if you are mapping between two different vector spaces, right? For example, I'm going to define what surjective is, but we're going to do an example in just a little bit that's looking at a transformation from P2 to M2 here. This transformation, the domain and the codomain, the additive identities are different, right? Here, the additive identity 0, P2, this is just 0, right? The 0 polynomial. But here, the 0, so like 0 M22 is equal to a 2 by 2 matrix, right? And certainly a 1 by 1 matrix cannot be equal to a 2 by 2 matrix. So, you know, it's important to specify sometimes that you're looking at different additive identities once we start to study this stuff in a much more generalized context. Okay, so and this may be the best way to show injectivity, is to just show this property here. Before we do an example, let's define surjective. So here's a definition. T from V to W is surjective, or onto, if for all elements of the codomain, so for all W in capital W, there exists an element in the domain, so there exists V and V, such that W is equal to T of V, right? And again, what does this mean? This means, you know, if you have V here, W here, and you map under the map T, you get that the image is a subset of W. This cannot happen. This cannot happen for a surjection. Right? What does this mean? Right? Well, here what I've written is like, you know, we have the map T, and this would be to say that the image of T is a proper subset of W. But that cannot happen for a surjective map. Surjective maps are those where the image is precisely the entirety of the codomain. So this is, you know, like if and only if the image of T is equal to W, not some subset, right? And so if you had, like, here's V, here's W, you know, this would have to map to all of W. Not one-to-one necessarily, right? I could have multiple points map to just one point. As long as every other point is also mapped to, that's a surjection, right? It's not until you require one-to-one and onto that you get an isomorphism, right? So just to try and remind ourselves and be very explicit about injective and surjective maps and hopefully increase our understanding. So let's look at an example. Let's say S is the map from polynomials of at most degree 2 to the set of all 2 by 2 matrices. Let's let this be a linear transformation. Given by S of ax squared plus bx plus c is equal to a plus b, a plus c, b minus c, b plus c for every polynomial in the domain. So let's show that S is 1-to-1 or injective, but not onto, right? So how do we show that something is 1-to-1? Well, we have to show that if under the image, you end up with the 0 element, right? So i.e., to show that it's 1-to-1, let's say for 1-to-1, we need to show that S of ax squared plus bx plus c equals 0, 0, 0, 0. We need to show that this implies that a equals b equals c equals 0, right? If we can do that, then we've proven that this is 1-to-1, because 1-to-1 maps, the only thing that gets mapped to the additive identity of the codomain or the image is the additive identity of the domain, right? So, i.e., we need that a plus b, right? We're looking here. We're looking that this is equal to 0. So a plus b, a plus c, and then we have b minus c, and then b plus c is equal to 0, 0, 0, 0. This sets up a system of equations. Well, then we have a plus b is equal to 0. We have a plus c is equal to 0. We have b minus c is equal to 0. And we have b plus c is equal to 0. We can try to, right? We're trying to solve the system of equations and verify that a equals b equals c is the unique solution here. Well, what would this augmented matrix representing the system look like? It would be 1, 1, 0, 0, and then 1, 0, 1, 0, 0, 1, negative 1, 0, 0, 1, 1, 0. You can put this into reduced row echelon form. Good exercise as the final approaches, because, right, you won't necessarily ask to just like a given question won't just be put this in reduced row echelon form, but this may certainly be part of a problem, right? So good practice. Once you put this in reduced row echelon form, you do indeed get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, which implies that A equals B equals C equals 0, which implies that S is 1-to-1. Now, how could we show that it's not onto, right? To show that it's not onto, we need to find some values, right? We need to find some values such that this system would be undefined, because we are looking, right? So let's just write this out. To show that S is not onto, we need a matrix, a 2x2 matrix A, such that S of P of X is not equal to A for any P of X in P2, right? Because to show that something's not surjective means to show there's at least one element of the codomain that is not in the image. So how can we do this? Well, basically, one way is to just kind of guess and check. But really what we're trying to do is set, like, you see here we took this matrix and we set it equal to all zeros. Basically what we would need to do is set up a matrix, or set this equal to a matrix, and then see if there's a solution or not, right? So let's look at A is the matrix 0, 0, 1, 2. Well, if we set then A plus B, A plus C, B minus C, and B plus C equal to A, 1 or 0, 1, 0, 2, this gives us the following system, right? We would have A plus B is equal to 0, so 1, 1, 0, 0. And then we would have A plus C is equal to 1, so 1, 0, 1, 0. We would have B minus C is equal to 0, so 0, 1, negative 1, 0. I don't know why I wrote 0 here. You should be a 1. And then we also have that B plus C should be equal to 2. If you put this into reduced row echelon form, you get 1, 1, 0, 0, 0, 0, 0, negative 1, 1, 1. Well, you don't get this in reduced row echelon form, but you get it as reduced as possible, which is this here. And what you end up seeing is that this has no solution. This implies that A, which is equal to 0, 0, 1, 2, is not an element of the image of S, but is an element of M22, which implies that S is not on 2. So here's an example of a map that's injective, but not surjective. So let's look at an example of the flip. Let's find an example of something that's surjective, but not injective. So let's look at T from M22 to R2, given by T of A, B, C, D equals A plus D, B plus C. Now, we want to show that T is onto, but not 1-to-1, okay? So how can we do this? Let's show it's onto first. Well, let's consider xy an element of R2 for all xy in R, right? That's every possible element of R2. Well, then consider the element xy 0, 0 contained in M22. Then what is T of xy 0, 0? Well, by definition, that's A plus D. And here, A is X, D is 0. Same for B and C, which is xy, which means for any vector in R2, there exists a 2x2 matrix such that the image of that 2x2 matrix is the specified vector. That's exactly what it means for T to be onto or surjective. Right? Okay. How do we show it's not 1-to-1? Well, to show it's not 1-to-1, it would suffice to show, so to show T is not 1-to-1, it suffices to find a non-zero, or let's just say, find a matrix M which is not 0 such that T of M equals 0, right? Well, we're looking at the map T of A, B, C, D equals A plus D, B plus C. If we want this to be equal to 0, 0, we get this anytime this holds anytime that A equals negative D and B equals negative C simultaneously. So let's let M be the matrix and whatever, right? Let's let A be 5, so D is negative 5, and then B be 2, so C is negative 2, right? Well, then this is certainly not the 0 matrix, but T of 5, 5, 2, negative 2. Sorry, that should have been a negative. This is equal to 5 minus 5, 2 minus 2, which is equal to 0, 0, which implies that T is not 1-to-1 or injective. Right? So there's now an example of a linear transformation of vector spaces that is, well, the first one was injective but not surjective, and this one is surjective but not injective. So what we're going to do next is we're going to look at what happens when they are, so what about a transformation that is injective and surjective, right? Well, we call these bijective, and we also call them isomorphisms. And so in the next part, now that we've re-explored and kind of gone over some examples for vector spaces in general of what injective and surjective maps are, what they look like, some examples, right? We're going to do the same thing for bijections or isomorphisms.